Hello, everybody. This is Electricity and Magnetism course. We are on the second chapter, Gauss Law. Okay. The first thing we have seen in the previous chapter is that for the point charges, the electric field lines were straight in three-dimensional space, homogeneously distributed in space. Okay. So the electric field lines are always away from the positive charges, but always towards the negative charges. For the surfaces, say circular surface, if we place the charges on the surface, okay, we see that electric field was given by sigma over 2 epsilon 0, sigma being the surface charge density, which is Q over area, okay, area. For the cylindrical case, area is pi r square, of course. And the electric field was given by this expression, where the point is measured from the surface is x. When x is very small, you can ignore this part, and then you can see that the electric field is given as sigma over 2 epsilon 0. So we were able to use this as an opportunity to get some kind of capacitor, okay? One side is coated by positively charged, okay? And the other side is negative charge. And inside there is an electric field kept, but outside electric field was 0. So this is the regular property of the capacitor. However, we know that if we look at this system from the side, this is exactly what we see. This is plus charge and this is minus charge, okay? And the electric field line inside is from plus to minus, of course, this way. And the magnitude was given by sigma over epsilon 0. The reason that there is no 2 here on the denominator is because the electric field has two components coming from the positive charges and negative from the negative charges. And if you just add these two up, you get sigma over epsilon 0. So this is the case. It doesn't matter what kind of surface you have. You could also have the rectangular surface as far as they are loaded in with opposite charges. Then the electric field inside will be exactly sigma over epsilon 0. We also want these two surfaces to be as close as possible, almost touching but not touching, because if at any part these two surfaces touch each other, all the charges just replace, the electrons go to the positive charge, and then everything becomes neutral. So in this case, we don't have any capacitor anymore, and the system just goes away. Okay, the system does not act as a capacitor. Okay, but in order these surfaces not to touch each other, usually we put some kind of dielectric, okay, in between. Okay, probably a little bit larger so that the edges also will not touch. So this dielectric will increase the dielectric strength inside the system, okay, so that you can really make them so tightly packed. In this case, the distance will be as small as possible, okay. The electric field intensity will increase. So this is how the capacitors are done. We have seen that, okay, we have seen that the electric field lines from the surface, from the flat surface, was straight, okay, but when you get close to the edges, the curvatures start, okay, like that. So also when we have like plus and minus charges, plus Q and minus Q there, and we know that the electric field lines always have this kind of curvature. But when you look at the electric field lines near each positive or negative surfaces, they are all straight like that, okay? But when they go outside, they immediately, okay, connect the other one so that they are aware of each other. So if you bring the two charges together, the electric field lines will just match, okay? Will just catch each other, and then we will have some kind of curvatures in the electric field lines, okay? So electric field lines may have curvature, But we will see that in the next chapters, magnetic field lines are almost always curved. Okay. So these sides of the charges do not feel each other. Okay, because they are screened somehow. Okay. So now let's put another surface in a curved electric field and see what happens. Okay, see what happens. Let's assume that the electric field lines are in this direction, and we place a surface like that. Okay, surface. So the electric field lines will pierce through this surface and go to the other side. Okay, and of course we are dealing with non-metal surfaces, let's say. So this is, we will see that this will be an hypothetical surface. So we will just assume that there is a surface, but this will help us to calculate the electric field line distributions due to the continuous charges. Okay, so this is surface. This surface is totally perpendicular, as you see, to this electric field lines. In this case, we will be able to catch all the electric field lines, okay, passing through the surface. But if you start to bend the surface a little bit, okay, although the electric field lines are again in the same direction, but now we bend the surface so that now we have this way, okay, the surface is like that, okay. As you see, now some of the field lines may not be able to be caught, okay. So because the reason is that when the curvature increases from the top to the bottom surface pictures, okay, like this, now it's now, as you see, dramatically rotated. Some of the field lines will not be able to pass through it, okay. So here only 3 lines, here 4 lines, but 5, 6 lines are passing through the surface. As the surface is bent, the number of electric field lines passing through the surface will be reducing. In this example, if the surface is totally parallel to the electric field lines, there is no electric field lines piercing through this surface. That's why when you rotate the surface like this, okay, the number of electric field lines will be reducing depending on the angle. So for the angle, we assume the perpendicular area vector, okay, the surface area vector, and we call this as A. This area vector, as you see, will be always perpendicular to the surface, and it will follow the rotation, okay. So this will help us to calculate how much of the electric field lines will pass through the surface, okay. So the surface area vector, as you see now in the last example, is totally perpendicular to the electric field lines, okay. Okay. Now, as you see, you remember from the vector product, if the two vectors are dot multiplied and the result is 0, then it means that vector x and y are perpendicular to each other. It's like that, right? So now this is, suppose this is x vector and this is y vector, and if they are perpendicular to each other, their dot product is 0. Because the dot product tells us that x dot y is equal to xy, the magnitudes, times cosine alpha, where alpha is the angle between them, okay? So if x is this way and y is this way, two vectors, and the angle between them is alpha, then the vector product, dot product, actually tells us that it's just xy cosine alpha. Now, as you see, you can think of this 2 ways. You can project x onto y, and then this becomes x times cosine alpha, and you multiply x cosine alpha by y, or let's draw the same vectors again, okay? You can now extend this a little bit, and then now project y onto x, but this is now, this part is y cosine alpha, where the angle is again alpha. So you multiply the components which are parallel to each other, which gives you xy cosine alpha here, y cosine alpha x there, which is the same thing. So this dot product actually deals with the projection of one vector onto another. If the vectors are totally perpendicular to each other, the projection is obviously zero. Okay, so the projection of this perpendicular vector at the other vector is just going to be a point, which is dimensionless, and we assume that it's zero. Similarly, for this case, we dot product, okay, electric field lines by the area vector, and we call this as flux. So this is flux. But we will see that this is electric flux. There are also magnetic fluxes, we will see, okay? So when the electric field is passing through a surface, then there is an electric flux. Some is suppose that we have a surface rectangle area which is 10 centimeters by 10 centimeters. Okay, in this case the area is given by the product of these two numbers, and the electric field is also given as 200 Newton per coulomb. Okay, so in this example the areas are given. So but the area, for the area, we don't just multiply 10 by 10 because we have to convert this into meters. Okay, so it's actually 0.1 times 0.1. So the result is 0.01 meters squared, and we multiply these two so that we will see that it's just electric field is just 2. Okay, the electric flux is just 2. Okay, what's the unit of the electric flux? As you see, it's this electric field is, the dimension of the electric field is Newton per coulomb, and then the area meter square. So Newton meter square per coulomb. We will see that this is also equal to charge divided by epsilon zero. Anyway, but now let's assume that the area, this angle is like theta. If the angle is, in this example, the angle is 0, right? Theta was 0 degrees. But if the angle is 30 degrees, then the flux is given by E times A times cosine 30 degrees. So we multiply phi will be equal to 2 times cosine 30, which is square root of 3 over 2, and it's just the square, it's just square root of 3. Okay, and the unit is again Newton meter square over coulomb. Okay, so this is the example that we solved, the first example. Now let's introduce the Gauss's law now. Gauss's law states that, okay, if there is a surface like that, okay, doesn't matter. It may have three-dimensional included inside this Gaussian surface. It's Gaussian, okay, surface. Okay, the electric flux, of course, suppose that there is a point charge inside. Okay, so the electric field lines will go and pass through this surface. Okay, not necessarily at the same angle at each point. Okay, so here, for instance, the electric field lines is this way, but the surface area vector is that way. Okay, perpendicular always. As you see, there is an angle between them. But here, the electric field lines is this way, and the surface area normal is almost in the same direction. So maximum flux here, but just a little bit flux. But if you look at this part, okay, this part, the area vector is this way. But now if you draw a straight line to the center, okay, and the electric field lines is that way. So the angle between them is almost 90 degrees, so that very small amount of flux is passing through this point. So, but now what we can do, because this is a Gaussian surface and it's a continuous surface distribution, and we have to add each contributions up, okay? So we have to get all these points and add them up in order to get total flux. So, but how do we do this? So if this small area is delta A, okay, vector, and this small area is delta A vector, okay, another delta A vector, okay. So electric field lines, of course, changing with the distance also. In this case, we could just add them up, all the contributions. So we just dot multiply by this small area vectors, just add them up. I equals 1 to n, maybe n of them, okay? And we call this as flux. But now, if you go, if you want to be more accurate, the surface areas, okay, surface areas can be reduced to 0, very small, so that we can see that we will be very accurate by getting more and more points on the surface when the area, surface area is reduced. In this case, when the limit delta A approaches 0, then the integral or the summation E dot d delta A's, okay, just approach to integral E dA. So this is the definition of course, there is a dot product between the two vectors. So the definition of integration comes from this fact, okay? So we make the surface, doesn't matter. One of them or both of them can be okay, can be curved or something. The result is just Q in over epsilon 0. So in or enclosed, let's say, it's better to use enclosed subscript. So this is enclosed charge. Okay, so this is also enclosed charge. As you see, this surface, which is Gaussian surface, okay, includes this charge, enclosed charge, okay, and then because of this charge, the total electric flux will be equal to 0. But now what happens? What happens if you put two charges together, okay, here? Suppose that we have now plus and minus charge, the same amount of charge. Suppose that one of them is here, the other is here, minus Q. Now we just covered the two charges everywhere in three-dimensional space, and guess what? The total flux will be equal to 0. Because why? Because the charge enclosed within this Gaussian surface is plus Q minus Q, which is 0. Now, if you have, for this case, if you have 2Q, for instance, plus 2Q minus Q, okay, and then 2Q minus Q gives you just Q, and the flux will be equal to, okay, will be just, suppose the surface area is just A, okay, somehow you can only calculate this by just dot multiplying this these two vectors, but this is not going to be 0. So it will be equal to just Q over epsilon 0. We know the right-hand side. It's very nice. So without solving, without looking inside at this shape, okay, we can really predict how much charge is included inside. Very nice. Suppose that there is an invisible ball, and inside this ball, there are some charges, okay? So there are many charges like plus 2Q, minus 5Q, okay, Q, and even different kind of charges. As you see, if you can calculate the flux, so here, calculate flux on the surface. Somehow, maybe we have a device, when you touch these points, you can get the total electric flux by the device, and then inside you find what kind of charge. Of course, they will add up and come up with some number. Here, minus 5q, 2q, q, which is minus 2q. You can find what kind of charge is inside the volume. This is a very powerful method. So you're not be able to see what's inside, but you can really predict how much charge is inside without looking. So these kind of equations or laws are extremely important in electromagnetic theory. So without looking, we can really predict what kind of charge is enclosed. So, but this is, don't forget, this is the Gaussian surface. But we can really, if we can find some symmetry, so if some symmetry is used, then we can use this equation like this, okay? So equation is given by this integral, which is equal to q enclosed over epsilon 0. Suppose that we know the charges, but we would like to calculate electric field from this equation. Actually, from this integral equation, we see that if you know the electric field, you put here and multiply by dA area vector. Suppose this is now dA. Let's use the red color. This is dA vector, but the dimension of this, or the size of this vector, is just dA. Okay, when you don't put any vector sign, it's just its magnitude. But if you put the vector sign, it's not only its magnitude, but also showing the direction. So now, if you know the electric field and if you know the area, you just dot multiply and add from all the surfaces, all these contributions, okay, little by little, and then you come up with this q enclosed over epsilon 0. Now, if you can catch some symmetry, so if area is constant on surface, on Gaussian surface, specifically selected, then we will see that if the electric field is constant, you can take this outside, okay, and then you have just dA like that. Dot product is outside or inside, doesn't matter, okay. So the electric field was constant, and this right hand side is q enclosed over epsilon 0. But now this gives you the total area, as you see this, because integration is the summation. So that now this is the total area, which is just A, okay, is equal to q enclosed over epsilon 0. Now in this case, we use this opportunity, okay, to be able to solve the electric field. But now we are going in opposite direction, because this equation tells me that when I look at this equation, I insert the electric field function here, and then the area vector function there, just integrate, and the result is given by the right hand side. But now if you use the symmetry, okay, very carefully selected symmetrical Gaussian surface we will use, then electric field will be constant on all the points on the surface, so that it's taken outside the integral sign, so that we are just left with the summation of all these little area contributions, which gives you total area. And we come up with this very first equation that we have written, okay? So the flux is just E dot A q enclosed over epsilon 0, okay? So now, as you see, we now learned how to use the Gaussian surfaces and the flux definition, and also the Gauss law. So Gauss law, let's keep this in here and then solve one example, very simple example. As you see, suppose we put a point test charge here, and now we know that from this point test charge, electric field lines are emanating in three-dimensional space, okay? Not only sideways, of course, in upper direction also, in lower direction, everywhere, okay? Like bonus head, you know? Okay, so now we would like to choose a very careful, we will choose a carefully selected Gaussian surface such that electric field lines are always are having the same intensity. What kind of surface should it be? Of course, it should be spherical surface, you know, because when the radius are the same, this is called Gaussian surface, which is in spherical. And the importance is this: if you choose any point like that on the surface like that, the distance from the center to this point will be just r, okay? R. The radius is always r. So as far as r is constant, we know that electric field is also given by k, okay, q over r square, because we have just point charge q, which is the charging included, okay, and closed charge, okay. So this will be also constant. As you see, q is constant, just sitting there, and the radius is constant, then the electric field is constant. Wow, okay, this is a good idea. But if we picked this point charge and a cylindrical shape, for instance, like that, as you see, now the distance, these distances are not going to be the same to the surface, okay? So the distance of this point charge to the surface here, there, and there, for instance, as you see, the distances are changing. So this was not a good idea. So this is not a practical, of course it's a Gaussian surface, we can choose it to make our life more miserable, but this is a much better choice. So we don't use this, so we just accept this one, okay? Because this Gaussian surface, although that this surface physically does not exist, we chose this surface such that the electric field on the surface is constant. Then look what's going to happen, okay? And not only the electric field is constant, but also the area vectors always away, okay? This is the area, dA vector, okay? Always perpendicular and in the radial direction, okay? So electric field and area in radial direction. In this case, in spherical geometry, I can write these two vectors in the radial vector form. So the electric field will be given as k q over r square, r unit vector. As you see, you need a unit vector on the right hand side. It's the only r unit vector you can use because this is it. R unit vector is always, of course, there is no unique r vector because there are infinitely many r vectors pointing in all directions in spherical geometry. But we know that whatever radius you are considering, it's in the same direction. And also dA vector is just dA times r unit vector. Now, if you dot multiply these two quantities, okay, like this, E dot dA is just kq over r square dA. Now we have r dot r. Now, when you dot multiply two unit vectors, it's just one. We know it, okay? We know it. Because it's the magnitude is one, the dot product is 1. But if you have two unit vectors like cross multiplied, okay, cross multiply like that, okay, then it's 0 obviously because they are in the same direction. The cross multiplication is 0, but the dot multiplication gives you 1. So because we knew it, because we chose these dA vectors in the same direction with the electric field, so that there is no vectors involved, there is no cosine theta or something like that. So E dot dA is just this, okay? There is no angle between them, okay? So the angle, electric field also in this direction, so the angle for this case is 0, okay? In this case, cosine theta is going to be just 1, okay? So now, in this case, the integral k q over r square dA, okay, dA will be equal to just right hand side will be just q enclosed over epsilon 0, okay? Now, what is this dA? What is this dA? dA is important, okay? In spherical geometry, the surface area vector is just to be written as 4 pi r square. As you see, this whole thing, because r is constant, it's not changing, you can take it outside, okay? So k q over r square integral dA, which is the total surface area, okay? Total surface area of this spherical Gaussian surface, okay? And it is obviously just 4 pi r square, right? So this integral dA is just 4 pi r square. So it's equal to k q over r square times 4 pi r square, because it's the total area. Right hand side is still q enclosed over epsilon 0. Now, what is k? Let's also write k here. Okay, k was 1 over 4 pi epsilon 0. Do you remember? Now look what's happening. R squares are canceling each other. 4 pi's are canceling each other. We have q over epsilon 0 on the left hand side, q enclosed over epsilon 0 on the right hand side. We see that we found it. Or we use this as an opportunity to solve the electric field. But in this case, we put the electric field values, and then we just show that really enclosed charge inside the spherical shape is just q. We found this, but now we didn't use this, okay, to solve for the electric field. Now, how could we do this? Suppose that we don't know this expression. In this case, do you know what will happen? We just keep this as E, okay, integral E dot dA. We know that there is no dot or vector dot product or vector signs are required. E dA, but E is constant, take it outside, is equal to Q enclosed over epsilon 0. In this case, E integral dA will be given right hand side, equal to the right hand side, epsilon 0. But now the total area, the total surface, this is total surface area of Gaussian surface, which is again 4 pi r square. Now from this, electric field will be Q over 4 pi epsilon 0 r square, which is just K Q over r square again. Okay? Now, as you see, there are two different strategies. In here, in this example, electric field is used, but we have seen that it's constant taken outside, but here E is not used, because we know electric field is constant taken outside. We don't even know what kind of function it is. In this case, if you just get the total area and put to the right hand side, we were able to see that electric field is just K Q enclosed over r squared. Okay, and exactly this is just the electric field that we have solved for point charges. As you see, we are now using the Gaussian surface. If electric field is known, you insert and integrate, and the right hand side is equal to that one. But if you do not know the electric field, but you have to somehow introduce some kind of symmetry between the electric field and also the area vectors, so that the electric field can be taken outside, so that the procedure allows us, okay, to solve the electric field if the total surface area is calculated somehow. Okay. Now this is the end of the recording.